Whether it's been raining for just a few hours or for 40 days and 40 nights, if the sun appears and raindrops are still in the air, the world is treated to one of nature's most vivid spectacles, the rainbow. Imagine the mixture of fear and wonder that ancient people must have felt on seeing such a sight. These days, the wonder is still there, but certainly the fear has lessened as we understand more of the physics involved in producing such a display of color in the sky. After setting aside the awe, our curiosity produces question after question. Why is the rainbow a circular arc? What determines how high it is? Why are there colors? Why is there a special order to these colors? Why is there a second rainbow? And exactly where is that pot of gold? Today, we're reading Rainbows, explaining colors with math. The early explanations of the rainbow were understandably mythological in origin. The Greek goddess Iris was said to use the rainbow as a sign of both warning and of hope. The word iridescent probably comes from the connection to Iris. In African mythology, the rainbow was a large snake coming out to graze after the storm. Here again, the event is a sign of both hope and one of fear. Yet in a less capitalistic vein, many American Indians saw the bow as a bridge anchored in this world and leading to the next. In ancient Greece, Aristotle used careful geometry but faulty reflection laws to establish the circular shape of the bow. Gradually, scholars began to see that both reflections and refraction of light had something to do with the rainbow phenomenon. In the 14th century, theoretic of Friedberg and Persian scholar Kal al-Din al-Farisi independently decided that raindrops were the key. They looked closely at the way the globes of water affected light. The rainbow had its peak interest in many scholars, each in the last several centuries. The 16th century seemed to have produced most books on the subject, but few of them were of major importance. As you might suspect, 17th century scholars like Kepler, Descartes, Fermat, and Newton all made significant contributions to the study of the rainbow. Light from the sun, refracted and reflected by water droplets in the atmosphere, forms the rainbow, so the first step in explaining the phenomenon is to understand how light is bent around various substances. In 1657, the mathematician Pierre de Fermat turned his attention to the bending of light and proved the main result by postulating a simple principle. Light follows a path which minimizes the total travel time. This is Fermat's principle. In calculus, one studies the maximum or minimum of a function, the relative extrema, and this is called optimization. In order to understand the behavior of light, we first look at how reflections work. We make our first assumption by assuming that light travels along rays. This will allow us to set up some geometry. So consider a point source of light, P, that is a distance, lowercase p, above a reflective surface. A ray, representing a light ray, comes down and will reflect off this surface at point R, and then be detected at some point Q, which is a distance, lowercase q, above the reflective surface. Setting up another perpendicular here at the point of reflection, the angle alpha is what we'll call the angle of incidence. and it is equal to this angle over here by symmetry. Angle beta will be what we call the angle of reflection. And again, by symmetry, both of these angles are beta. Now you can appreciate that we have a right triangle situation here, so let's call the distance between points P and Q the distance d. And the distance to the point of reflection R we'll call x, making the remaining distance d minus x. We can then use the Pythagorean theorem to find the length of the two hypotenuses in red, which are the paths of the light rays as it is reflected. So we can ask the question, at what point R does the light ray reflect off the surface? And here's where we'll want to implement something called Fermat's principle. Fermat's principle was that light travels the path that minimizes the travel time. That is, that light will travel along the path that is quickest. So in the world of calculus, we say that we want to minimize the time it takes to traverse the path PRQ. Alright, so we have to go into a little detail here with introducing Albert Einstein. In his theory, as his formulation of the special theory of relativity, Einstein took a guess that the speed of light, we'll call c, was constant. Another way to say that is that light does not accelerate. So light is constant in all reference frames. This was the basis for his special theory of relativity, and it will become important in our calculations. Now, the fact that the speed of light is constant was confirmed empirically by the famous Michelson-Morley experiment. So now, assuming that the speed of light is constant, to minimize the time will show as equivalent to minimizing the distance. You see, if the speed is constant, minimizing the time here is proportional to minimizing the distance. So in order to minimize the path of quickest time, we need to find the path that minimizes the length of our path. So now let's derive an expression for the length of our path. Let's let L be a function of x, and it'll be the sum of the two paths in red, which we found the lengths of using the Pythagorean theorem. Now what we'll need to do to minimize this path is use the first derivative and set it equal to 0. Finding the minimum will be about finding the critical point x that minimizes the path. Now the derivative of this expression will require you to use the chain rule of differentiation. But once we clean up the expression that we get, it works out to be something very nice. L prime of x is x over square root of p squared plus x squared minus d minus x over the square root of q squared plus d minus x squared. And if we set this thing equal to 0, then we can just move one of those parts to the other side of the equation. Now, we could easily solve this equation for x and find the critical point. Here, x works out to be pd over p squared plus q squared, but that's not really important here. What we want to notice is that we can rewrite this equation in terms of the trigonometric expression of sine of alpha and sine of beta. And the left-hand side is the sine of alpha, the right-hand side is the sine of beta, and given that alpha and beta are in the range from 0 to 90, that implies that alpha equals beta. So this equation, the minimizing of the path, implies something we will now refer to as the law of reflection. The law of reflection states that the angle of incidence alpha is equal to the angle of reflection beta. An important geometric result. Next, we must consider a concept called refraction. Now, refraction occurs when light passes through two different mediums. The speed of light passing through water is actually slower than the speed of light passing through air. So we have two different mediums to consider when light is passing through air and then hits water, a raindrop. Now, the difference in the speeds of light will make a difference in the minimizing of the path it takes, or the time it takes for the light to travel. And it will cause the light ray to bend or refract. So you may have noticed refraction if you've ever stuck your hand into a pool. It looks like it bends your hand in a weird angle. Okay, so let's set up a situation similar to before. We have a point source P of light where a light ray is going to come down at a point R, which in our first example was the point of reflection at angle incidence alpha. But now our light ray is going to pass through water. And so water has a different density than air, and therefore the speed of light is different, so it will actually bend the light ray away. Now, as before, the geometry where it is detected at point Q creates two right triangles in our picture. And again, here's a picture of an example of refraction. The angle that is formed when it is bent, we'll call that angle beta, and that we'll call the speed of light through air c sub a, and the speed of light through water c sub w. So we have two angles to consider: the angle of incident and the angle of refraction. Okay, so let's consider the path that is now created because of these two different speeds of light. Again, moving through different mediums, we're going to consider what happens as that path is altered. So the path from P to R through air takes a time, which is distance over speed, of the square root of P squared plus X squared over the speed of light through air, so C sub A. Once it hits water, the path through R to Q will have distance over speed to be the time as the square root of Q squared plus D minus X squared over the speed of light in water. Total time traveled will be the sum of these two things. So let's call that our function t of x. Now, like before, we want to find the minimizing time, so we want to take the first derivative, set it equal to 0. Taking the first derivative, again using the chain rule. Here, one of the only differences is we have these two different constants to consider, but what that's going to allow us to do is to consider when we rewrite this equation in terms of its trigonometric components as we did before, we get the following relation, something similar to the law of reflection, but this says here that the ratio of the sine of alpha, the angle of incidence, over the sine of beta, the angle of refraction, is equal to the ratio of these two speeds, which would be a constant, and so the ratio of the sines is equal to this constant of the two speeds of light. In the world of optics, we call this the index of refraction. And the law of refraction states that the sine of the incidence angle over the sine of the refraction angle is always constant. So this constant we could perhaps refer to as just a constant k. And for the value of the speed of light in air versus the speed of light in water, this constant works out to be approximately 1.33, the index of refraction. For a different medium, we would calculate different values for the index of refraction. Next, the rainbow angle. At what angle should we expect to see a rainbow? So consider light passing through a spherical drop and reflecting off the back, and let's take a look at the geometry that would ensue when this happens. So at point A, where the light ray enters the light drop, we have an angle of incidence of alpha, and then it is bent, refracted, by an angle beta, which we can follow the geometry through, and that angle beta is repeated. And it exits at point C, and now we can figure out what is the angle of what we would call deflection. The angle at which this ray of light would exit the drop of water, but at a different angle. So it seems to take this angle that's coming in, and inside the drop it rotates it a bit, and then it comes out. So let's consider if it came in just exactly along the diameter of the drop. It would return by just bouncing off the back at a 180-degree rotation, so we could say that the angle of incidence was 0 degrees and the total deflection angle was 180 degrees in a clockwise directional turn. So that's only if it enters directly along the diameter. And as alpha varies between 0 and 90 degrees, we get a function of alpha, which we can call the deflection function, or the angle of deflection function. So the ray that is deflected at A gets rotated a number of times through a certain number of angles in clockwise directions. So let's see if we can follow that path along. At A, it gets rotated an angle of alpha minus beta degrees. At point B, it then gets rotated at 180 minus 2 beta degrees, in again the clockwise direction. And finally, at C, it will get rotated another alpha minus beta. So we can therefore write something of a deflection angle function by adding up all those rotation angles. Here, alpha minus beta plus 180 minus 2 beta plus another alpha minus beta. So that deflection angle of that deflection function of alpha is 180 degrees plus 2 alpha minus 4 beta. All right, so what does this tell us about the story of that light ray? Well, from the law of refraction, we can rewrite or express beta in terms of the angle alpha, right? There's that connection between those two things in terms of their sine of those angles, right? So let's also note that when we enter at 0 degrees, we get a 180 degree deflection angle. And then as alpha increases, we see, at least at first, a decrease in that deflection angle, but then it will begin to increase. That will indicate that d of alpha has a minimum at that value. So d prime of alpha, when we differentiate it with respect to alpha, we'll get 2 minus 4 d beta d alpha. And using that refraction law of the sine of alpha over sine of beta being that constant k, we can write a few things out by differentiating that equation and then incorporating it into our derivative. Right, so taking the fact that sine of alpha over sine of beta is equal to k, we can differentiate that and get cosine alpha is equal to k cosine beta d beta d alpha. And so we solve that for d beta d alpha, and we're able to substitute that back into our derivative for the deflection angle. So we get 2 minus 4 times cosine alpha over k cosine beta. And then what we're going to do here is we're going to, again, set the derivative equal to 0 to minimize the function. Now, when we do this, we are going to be able to manipulate this equation to read as k over 2 equals cosine alpha over cosine beta. We're going to have to now rewrite this, and the trick here is we're going to actually square both sides. Why are we going to do that? Well, because we're going to use the cosine squared of beta and replace it with an identity, a trigonometric identity, 1 minus sine squared beta. And from that law of refraction, sine of alpha over sine of beta equals k, we can do a little bit of substitution with that law into this expression so that sine of squared of beta can be written as sine squared alpha over k squared. Okay, so a little bit more algebra here and substitution. We can rearrange this equation nicely and write it in terms of cosine alpha is equal to the square root of k squared minus 1 over 3. Or alpha is equal to the inverse cosine of this radical. Okay, so our index of refraction was 1.33. So if we substitute that into our equation, we can get alpha to be approximately 59.56 degrees. So if our incident angle is 59.56 degrees, what is our deflection angle? Well, calculating that, we get approximately 137.5 degrees. So that is the deflection angle we get. And we're now going to put this into some sort of perspective to understand what that means. So the rays will be, well, they'll be brighter at this particular angle, or brightest at this particular angle. So we'll see what that is at that particular angle the most. It will be the least spread out, the light. Okay, imagine you as the observer standing here with the sun behind you. Now light rays coming from the sun are going to hit a water droplet, a rain droplet. So imagining this incoming ray, you as the observer look up, and you will see the light at the deflection angle of 137.5 degrees, shown here. Now, if we went a full 180 degrees, we would have to make up a difference of 42.5 degrees, and that would be the same angle of elevation that I would have to look up at to see our rainbow. This is called our rainbow angle. It is the supplement to 137.5, and that's the magic angle at which we will see our colors. So the next logical question comes up.
R is for red, O is for orange, Y is for yellow, and G is for green. B is for blue, I for indigo, B is for violet. That spells Roy G. Biv. Roy G. Biv is a colorful man.
Where do the colors come from?
At the rainbow's end. Roy G. Biv is a colorful man, and his name spells out the whole color spectrum.
Where do the colors come from? Light is an electromagnetic wave. As a wave, we can therefore talk about the wave's frequency and a wave's wavelength. This is what we would call the wave characteristics. Because light travels in different frequencies and different wavelengths, there's a wide spectrum of colors. Now, our eyes are only sensitive to wavelengths in the range from 7,000 angstroms to about 4240 angstroms. Red light is perceived at wavelengths in the range of about 6470 to 7,000 angstroms. On the other end of the spectrum, light perceived as violet is in the 4240 range. Since the wave character of the colors are different, their refractive index will also be different depending on that color. Red light has a refractive index going from air to water of about 1.3318, where violet light is about 1.3435. So now we're going to have to think about calculating something called the minimum deflection angle. Now for red light, the minimum deflection angle is 137.7 degrees. For violet light, it's around 139.4 degrees. So red light and violet light will deflect at different angles, and therefore we will see them at different rainbow angles, red light at around 42.3 degrees and violet light at around 40.6 degrees. Now, the observer will see a circular arc, and the circular arc of red will be higher up, and the circular arc of violet will be lower down, and all the other visible light in the spectrum will be in between. And it is because of the fact that the different wavelengths will have different angles, we get an order to the colors. The acronym that you may have heard in high school to remember this order was Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. This is what we call the visible spectrum of light. But of course, electromagnetic radiation goes beyond this spectrum: infrared, ultraviolet, etc. Isaac Newton was one of the first people to make this careful calculation to explain the colors of the rainbow. Now, often accompanying a rainbow is a secondary rainbow, and this is what we call a double rainbow. Why is there a double rainbow? What happens when light reflects more than once inside a raindrop? So imagine here the path of light reflecting twice before exiting the raindrop. If we set up the geometry and the angles here, beta being the angle of reflection, and alpha being the angle of incidence, we can write an expression for the total deflection angle when light reflects inside the water droplet more than once. So here we get alpha minus beta plus 180 minus 2 beta plus another 180 minus 2 beta plus another alpha minus beta, which is 360 plus 2 alpha minus 6 beta. And from a clockwise perspective, we can just multiply this by -1 and get 6 beta minus 2 alpha. Noting that at 0 degrees we get a deflection angle of 0, and that this particular deflection angle increases as alpha increases initially. So we get an alpha of about 71.94 degrees and a deflection angle of almost 130 degrees. So our double rainbow angle works out to be around 50 degrees. And this double rainbow will be a little bit less intensity than the first rainbow at 42.5 degrees. And that dark band between the two rainbows is known as Alexander's band. A great name for a band indeed.
Oh my gosh, it is a double rainbow. I cannot believe it. It's a freaking double rainbow. Oh my gosh, oh my gosh, look at that, all the way. Oh my heck, it's a double rainbow. Hey Cal, look at that, it's a double rainbow. Oh my gosh, it's a double. Hey Cal, where you going? It's a double rainbow. Look, it goes all the way. Oh gosh, I can't believe it. It's a double rainbow. I've never seen one of these in my life. It's a double rainbow. I cannot believe a double rainbow. I've been waiting so long to see look, all those colors. A double rainbow with all those colors. Holy cow. No offense. Holy cow, a double rainbow.